So finally, it's good to recap some of the issues. Just to start with the technological barriers, we want to inject these sulfate or other aerosols at about 20 kilometers. The existing aircrafts, especially the large cargo and passenger aircraft, which can be easily modified to carry the aerosols to spray into the stratosphere, are right now not designed to go up to that altitude. Okay, so this is the beginning point. The other ones that we considered, the spy plane U-2 and so on, have to be modified to be able to carry sulfate aerosols. Or if you wanted to use fighter aircraft which can fly high, then they are too small to carry big loads. The other option we looked at is to have balloons that can easily be sent up and are sent up to measure certain stratospheric properties and so on by NASA, etc. But they are not designed for carrying payloads, so then you would need this idea we saw of having a pipe that's going up to them at 20 kilometers and constantly pumping aerosols into them that then they can spray into the stratosphere. So then the cost is of course an issue. Most of these things to build and operate would cost around 10 billion, and then there is annual operational cost and annual cost of sending up sulfates and so on and so forth, manpower, etc. let's say. Okay, these are things that must be considered. So in other words, sustained plans to actually do this haven't been completely mapped out financially, but there are groups working on this seriously, so it's pretty clear that ideas are being tossed around and something will be tried pretty much. As I said, US was recommending something from the National Academy, but everything has suddenly gone quiet. But there is a webinar on May 26th of 2021 to discuss some of the science issues. Aerosols have to be small enough to effectively scatter sunlight per unit volume. The smaller they are, the more effective they are in scattering, and if the chemistry works out in such a way that they clump up and form bigger aerosol particles, then their efficiency in reflecting sunlight goes down. So this is something that has to be considered. So then the other idea considered is that instead of spraying sulfide, which has to go through reactions to become sulfuric acid in the cold temperatures where water droplets are condensing and so on, will sulfuric acid basically take out this middle step and make it more effective, more efficient? That is something to be looked at. There are also ideas to consider aluminum and titanium oxides, but as we said, these are not naturally occurring. For this we have guidance from volcanoes, and we have data, we have a good idea about impacts, but these we don't know. We just know that the optical, chemical, and physical properties allow them to be good at scattering sunlight and doing the solar dimming. Okay. There are details about forward and backward scattering. So sulfuric acid sulfate aerosols, which are formed from there, are good at forward scattering compared to backward scattering, which actually tends to give the sky a washed out look, like this painting the screen that we saw. This diffuse attenuation can actually help some plants, but not all of them. But this would definitely have an effect of reducing solar power production at the solar power plants, for example. So there is a price to pay in terms of reduced solar energy as a part of the renewable energy resource for the Earth. Aerosols may heat the lower stratosphere and make the tropopause more permeable. Remember, the boundary between the troposphere and the stratosphere is the tropopause, which is like a dryer which wrings out moisture before air can penetrate into the stratosphere from the troposphere. But warming the lower stratosphere because of the stratospheric heating by the aerosols can make the tropopause more permeable and cause more cirrus and long wave trapping. So we just talked about cirrus thinning and so on, but putting more water vapor into the lower stratosphere above the tropopause can actually worsen the IR trapping. So you have to be sure that you're not compensating for the solar dimming by doing these changes. So chemical, optical, and thermal properties of whatever substance we are going to spray have to be understood very well. Aerosol cooling will not be uniform. This is also true for cirrus and stratus decks, brightening clouds and thinning cirrus clouds. But veiling or solar dimming is also an additional climate change in addition to the greenhouse world. So it's not something that is an antidote to greenhouse warming, but it is on top of it. So we are increasing greenhouse gases, trapping more more outgoing long-wave radiation or infrared radiation. Solar dimming or veiling is basically reducing the incoming solar energy so that we just have to send out less infrared anyways. Okay, so we have to really be careful that the changes we talked about in terms of cooler temperatures, vegetation impact, carbon cycle impact, crop production impact, ozone hole impact, all those things have to be considered, coral impacts in the oceans, etc. Hydrological cycle right now, as best as we know, is accelerated by the greenhouse warming because warmer temperatures can hold more water vapor, but it also creates more rainfall overall. But as we saw with Pinatubo from the Trenberth and Dye paper, there were widespread droughts across the planet, so veiling or spraying aerosols into the stratosphere will make the planet drier. As we saw, the change in precipitation was about 5.1% for the greenhouse warming with no geoengineering, but it was brought down to 2.1% by the solar management. But we have to decide what will we compare when it comes to the impact of geoengineering. Will we compare the greenhouse world with the solar radiation management world with greenhouse warming, or will we try to compare it with the baseline where we are somehow without greenhouse warming, or we are comparing to business as usual? So the impacts of solar radiation have to be radiation management have to be considered carefully. So baseline planet to engineered planet or warm planet to the base planet comparison have to be decided. Engineered planet may reduce the so-called rich get richer, poor get poorer syndrome, which is basically that right now in the greenhouse world, the regions that evaporate and supply moisture to the regions that are wet is going to get worse, and the regions that are wet are going to get more rain, and there are lots of extremes in temperature and rainfall. So the good thing about the aerosol spraying is that it's going to reduce this exacerbation of the dry getting drier, wet getting wetter, and it's going to reduce extremes as best as we know from the model experiments. But productivity of plants increased in the engineered planet compared to greenhouse or baseline planets. So we will see this later in a later chapter, but the experiments that were done in the model to see how aerosol spraying will affect productivity of plants doesn't have full dynamic vegetation modeling. They do simplifications, so this has to be looked at more carefully, which we will do later on. Stopping the aerosol injection will create a terminal shock that I already showed. Rapid warming back to where it would have been would occur if suddenly the spraying is stopped because of terrorist attack, because of policy changes, because of natural disasters, and so on. But two things: one, redundancy can be built into the system so that you have other systems that can take over if one system is damaged, and also The experiments which concluded that this termination shock would be strong basically use spraying which is much thicker than what is expected if solar radiation management by spraying sulfates or other aerosols is actually to be conducted. So the models may be exaggerating the termination shock a little bit. Finally, the complex greenhouse engineered planet would still have uneven impacts. So we are combining greenhouse gas emissions that are continuing while we are using solar radiation management. So you have a combined world now. So the impacts will still be disparate. There will still be people paying a price. There will still be winners and losers. And adaptation plans have to consider this more complicated scenario of not just a greenhouse world, but also a greenhouse world with additional climate change due to solar dimming. Okay, the same models that are used for doing the projections can be used for this as well, but the physics uncertainties would be much higher because the impact of spraying aerosols into the stratosphere has additional physics and chemistry questions that have to be answered by these models, which are already quite strained in terms of their uncertainties for the future.